In a previous thrilling episode, I said that I'd broken my continuity tester. So I thought I'd give you all a laugh and show you my continuity tester. And this isn't it. No, that's not it. This is my continuity tester. Go on, have a good laugh. It's homemade, of course. I built it in the late 1980s, and it's actually been very, very useful, even though it looks silly. I've used it constantly. Impressive, isn't it? There's a little hole there for the sound to come out of. I suppose you want to see what's inside it. Well, we can arrange that. Up. Off comes the lid. And that's it basically. There's a pair of batteries. There's a little blobby thing there with some electronics in it. And there's a little earpiece there for the sound to come out. So why all this electronics? Looks a bit of an overkill, doesn't it? Well, you'll have to take my word for it, because my other continuity tester is really broken. But a normal continuity tester just goes squeak. A continuity, no continuity. That's all you get. Squeak, squeak. Now, if you put a short circuit, squeak. If you put a 10 ohm resistor, squeak. Put a diode junction, squeak. All the same squeak every time. You might think you've got continuity, but what you might be measuring is a low value resistor, or a bulb, or even a germanium transistor junction. So, what is this one? Why is this one different then? Now, this might be a little difficult to hear, but here's the short-circuited. And here's what a bulb sounds like. Did you hear that? Okay. And what about a resistor? Well, this is a 10 ohm resistor, which on most continuity testers would just give a straightforward bleep, just the same as any other. Sounds pretty much short circuit, doesn't it? Unless you compare that. So let's test it with a slightly higher value resistor. This is a 47 ohm. I don't know whether you can hear that. That's short circuit. That's 47 ohms. Short circuit, 47 ohms. Let's test the transistor. Now, I don't know what transistor this is. I don't know whether it's PNP or NPN, so we'll just start by connecting the positive to one of the terminals and having a bit of a press around. Nothing. So both of those junctions reverse biased. So let's put the positive on that junction. And oh, look, we've got partial continuity to that one, and partial continuity to that one. So that's a PNP. Sorry, that's an NPN. NPN. And there should be no continuity between collector and emitter. No, there's no continuity. Shouldn't be any continuity the other way around at this voltage either. Nope, so that's a PNP transistor. Let's try this one. What's this one? Do the same again. Let's take a guess that the middle one is the base and connect that, and try the other two. Nothing. Nothing. Oh dear. So those junctions are both reverse biased. Let's try that one. Ah, continuity. No continuity. So let's put that one on there and try this one. So we've got continuity to that one and to that one, and they're both got continuity through some sort of diode junction to that one. So that's a PNP. Notice PNP. And we can also say this is germanium, because bringing the other one back, if you listen to the sound that this one makes, it's very difficult doing this through the camera. You lose all sense of depth. Notice that junction sounds low pitched, but this junction, remember that pitch? Higher pitch, less forward voltage drop. So let's try testing a blue lead. Oh, no squeaky at all. But you can see that it's the correct polarity because it's lighting the lead, but there's no sound. Incidentally, it's the same with an orange lead as well. It lights, but it doesn't squeak. Finally, here's a capacitor. So let's try this one. Listen carefully. I shall squeak this only once. Hear that little squeak? It doesn't squeak again till you short it out. No, it doesn't. I'll reverse bias it. Squeak, little tiny squeak. This is a 470 mic. Oops. It just gives a little tiny squawk. Here's a slightly beefier capacitor. A 2200 mic. Notice that? Woo! Let's reverse it and give it another go. Notice how it took longer that time because it was reverse charged. So if we turn it round again, it'll go long again. So that's what a capacitor sounds like. Now to me this is perfectly loud, but I realise you can't hear it very well, so I've stuck it in a plastic box. But you see, if you're doing some continuity testing on a piece of equipment, you can easily go so you can see that point there and that point there are connected, but these two aren't. But those two are. Those two are connected, but there's a low, and those two are connected, but there's a lower, there's a resistance between those two. So yeah, and you can see over here, you can easily find the ones that are connected. And it's much faster than using a meter, especially a digital meter, where you couldn't test. You couldn't test that quick with a digital meter. The point is, your hands are now free to do the job, and your ears are doing the interpretation. so you can keep your eyes on the job. Now here's another use case. You see this audio cable? It's there is continuity out there from tip to tip. Let me just hold that there. Okay. Now I'll move this cable. That's me just squeezing the cable. As you can see, the cable is intermittent and you probably would never know it. Now you try doing that with a digital multimeter or even an analog one, it would be difficult. You wouldn't know whether the variations were due to you not making proper connection or whether the cable itself was faulty. If you're interested, this is the circuit of the device. It's all based on the unijunction transistor. Well, come on, focus. And there's a 12K and a 47N. The 47N charges through the 12K until it reaches a certain voltage, and then the unijunction triggers. And when it does, it dumps the charge from the 47N into the earpiece. Then it starts to charge up again. So this makes an oscillator. The interesting thing about the unijunction, at a low voltage like 3 volts, it's very frequent, very voltage dependent. So if you've got a resistance across these probes, and you've got a resistance there which takes some of the voltage away, it means that this is operating off different voltages according to the resistance across the probes here. So it changes frequency, going lower in frequency the lower the voltage. Now, as you can hear, the downside is it's not very loud, and that's due to this little earpiece. Maybe it could have a much better device there and make it louder, but I've always found it useful enough. Anyway, sorry for the crappy audio and the shoddy camera work, but I thought you might like to see that anyway. If you like that, please give me a thumbs up. Bye!